We're going to go over another example of using spherical coordinates to compute a triple integral of a function of three variables. In this case, our domain of integration is the solid E, which is bounded above by the plane z equals 1 and bounded below by the cone z equals the square root of x squared plus y squared. The left-hand bound here is given by y equals 0. Okay, so it turns out that E can be described in a fairly straightforward manner using spherical coordinates. So let's analyze that right now. So the upper bound is given by the equation z equals 1. Now z is equal to rho cosine phi in spherical coordinates, so we get rho cosine phi equals 1, or that rho equals 1 over cosine phi, which is secant phi. So that gives me essentially the upper bound for rho, because really it's z is less than or equal to 1. So if I follow that through, I get rho is less than or equal to secant phi. Now of course the lower bound is going to be rho equals 0, and so for each ray coming out of the origin, I go from 0 up to this boundary z equals 1, which is really rho equals secant phi. Alright, so I figured out my rho bounds are between 0 and secant phi. Now how does the cone come into play here? Well, if I set z equal to the square root of x squared plus y squared, which is really just equal to the polar coordinate r in the xy plane, then again z equals rho cosine phi and r equals rho sine phi. So this comes from the right triangle. So if this is a point in R3, this is the origin, this distance is rho, this distance is z, and this distance is r, and then the angle phi sits inside this right triangle as such. So that's where these identities come from. So this equation means rho equals 0, or I have cosine of phi equals sine phi. And let's do like we did before. In the end, I actually have z is greater than or equal to r, so this is rho cosine of phi is greater than or equal to rho sine phi, and so this is cosine of phi is greater than or equal to sine phi. And if I divide through by cosine phi, I end up with tangent phi is less than or equal to 1. So I divided through, but I flipped the sides, and so you can follow along this inequality as tangent phi is less than or equal to 1, and that really means that phi is less than or equal to pi over 4. Okay, so what we find is that this boundary isn't really a bound for rho, it's a bound for phi, and it's phi equals pi over 4. Now we certainly have phi equals 0 because we have points along the positive z-axis. So that means our phi bounds are from 0 to pi over 4. Alright, now our theta bounds really come from y equals 0, and that gives us that theta is in between 0 and pi, the positive x direction and the negative x direction. Alright, so now we turn our attention to our function here, which is equal to 4 times the square root of x squared plus y squared plus z squared, but that's really just 4 times the square root of rho squared, and since rho is non-negative, we see that f is just equal to 4 times rho. Okay, so now we're ready to set up our triple iterated integral. So we have the integral from 0 to 2 pi. Sorry about that, the integral from 0 to pi. Then our phi bounds are 0 to pi over 4, and our rho bounds are 0 to secant phi. Now we're integrating the function for rho, and then of course we have to throw in rho squared sine phi, d rho, d phi, d theta. So now we've set up our triple iterated integral, and now we're just going to carry through with each iteration. Because there's no function of theta here and these bounds are constant with respect to theta, I can really just compute this integral from 0 to pi as giving me a factor pi. So I have the integral 0 to pi over 4, and then I have 4 rho cubed, so the integral of that d rho is rho to the 4th, and I have evaluated from 0 to secant phi times sine phi d phi. Okay, so I get the integral from 0 to pi over 4 of secant phi to the 4th. Now secant's 1 over cosine. I'm going to switch back to cosine. So I get cosine to the 4th phi in the denominator d phi. So we're left with this single variable integral to compute, and in this case we can accomplish this by u substitution. So if I let u equal cosine phi such that du equals negative sine phi d phi, and because I have this sine phi in the numerator in the integrand here, that means I'm going to be able to get away with this coordinate substitution. And you can check that in the end the antiderivative of this function is actually secant cubed phi. Alright, so that's the function we'll evaluate 0 to pi over 4. So we get pi, oh sorry, that's actually secant cubed phi over 3, because when I take the derivative I'm first going to get this factor of 3, which doesn't show up here, so I need to divide through by 3. So I get pi over 3, and then secant of pi over 4 is the square root of 2, so I have the square root of 2 cubed, minus secant of 0, which is 1 over cosine of 0, which is 1 cubed. So we have pi over 3 times 2 to the 3 halves minus 1. Alright, so we've computed this triple integral of our function 4 times the square root of x squared plus y squared plus z squared over this region E, which is sort of a portion of the cone cut off at z equals 1 and y at equals 0. And in this case we were able to use spherical coordinates, and it required a little more work to set up the bounds, but once you get used to these arguments, they work in a similar fashion for most of the examples that we'll encounter with spherical coordinates. So getting used to this problem will really prepare you for a lot of the problems that will come up in this course. And then once we translate it over here and set up this triple integral, then it's just a matter of doing the single variable calculus and iterating that 3 times to come up with our answer, which was pi over 3 times 2 to the 3 halves power minus 1.